Hey, what's up guys? This is Dr. Vivek Palipuram bringing you the next lecturette in ECPE 127. And in this lecturette, I'm going to cover some families of continuous random variables. And those families are uniform, exponential, and Erlang. These families appear quite frequently in science and engineering. And not only that, they also appear quite frequently in our day-to-day lives as well. In this lecturette, I'm going to show you some examples as to how these random variables are used to model some of the real life situations. Let's first start with uniform random variable. So x is a uniform random variable if the probability density function of x takes this particular form right here. F of x is equal to 1 over b minus a for x in an interval between a to b, and it is 0 otherwise. Now because b is the upper end of this interval, naturally b has to be greater than a. Now there is a very specific reason why a uniform random variable is called a uniform random variable, and that is because of the shape of its probability density function. So if you were to plot the probability density function of a uniform random variable between 2 points A to B, this PDF is going to be uniform. It's going to be a flat plateau right here. Not only that, the cumulative distribution function of a uniform random variable is a straight line between A to B. So it starts at 0. From A, it starts to climb uniformly until B, at which point it achieves a stable value equal to 1. So if you were to consider this CDF in this interval right here, you'll notice that the rate of change is quite uniform. It's always the same. And that's why it's called as a uniform random variable. Now there's very specific scenario where uniform random variables are quite useful. And that scenario is as follows. Let's say that you're modeling a random variable x, which is constrained to be in this interval, a to b, in this big interval between a to b. Now, if you were to consider any two sub-intervals of same size, then they are going to have the same probability. You're spinning the pointer problem actually is a uniform random variable problem because your pointer is constrained to be inside of a big interval between 0 to 2 pi. Now, if you were to consider any two slices of same size in this big interval, they are going to have the same probability. So if you were to consider any two slices of same size, they are going to have the same probability because theta, the angle at which your pointer is going to stop, is going to be uniform. Let's move on to the next random variable family, and that is the exponential random variable. X is an exponential random variable if its probability density function, small f of x, takes this very form right here. So far in our discussion in random signals, we have used lambda as a rate information. And this also holds true for an exponential random variable. Lambda here is some kind of a rate information or rate of arrival, if you will. And consequently, x happens to be the time elapsed until the first arrival or until the next arrival if you're already receiving certain items, or until the first success. So x is the time elapsed until the first arrival or until the next arrival that you're waiting on or until the first success. So in this way, it's quite related to geometric random variable, its discrete counterpart. So a geometric random variable models the number of trials until the first success. Exponential random variable, it models the time that has elapsed until the first success or until the next occurrence. So let's say, for example, that FedEx is going to deliver a package to me next. So the time x that I have to wait until the FedEx package is delivered is going to be an exponential random variable, which is going to depend on this parameter lambda, which is the rate of information, the rate at which the FedEx delivery system services its customers. So that's an example of an exponential random variable. Now the shape of the PDF of an exponential random variable looks something like this. Higher the rate, sharper the fall of the PDF of an exponential random variable. So here in this case, the rate of arrival is 1. So it has a sharper fall compared to other smaller rate of arrivals like 0.5 and 0.25. Let's now discuss Erlang random variables. X is an Erlang random variable that depends on two factors, n and lambda. And the PDF of an Erlang random variable takes this form right here. So f of x is equal to lambda to the n times x to the n minus 1 times e to the negative lambda over n minus 1 factorial for x greater than or equal to 0 and it is 0 otherwise. The expected value of an Erlang random variable is n over lambda and the variance of x is n over lambda squared. Now it is used to model those situations where you're waiting or you're measuring the time until the nth success. So for example, let's say that FedEx has certain rate at which it delivers packages. Rate of delivering packages. And further, let's say that I am n is equal to 5th customer. So if FedEx were to start delivering packages right from the very first customer, the time elapsed until I am serviced or I receive a package in this case is going to be modeled using an Erlang random variable. So in this way, it is quite related to its discrete counterpart, Pascal random variable. Now Pascal random variable, if you recall, is used to model the number of trials until the nth success. Erlang random variable, however, is used to model the time that has elapsed until the nth success. So that those are the typical cases where you would use an Erlang random variable. Now the probability density function of an Erlang random variable is quite different for different values of n. Notice specifically for n is equal to 1. N is equal to 1. When n is equal to 1, notice that the shape of an Erlang random variable is actually the shape of an exponential random variable. Now remember, n is the number of successes. So when n is equal to 1, you are modeling the time until the first success. And therefore, an Erlang random variable boils down to an exponential random variable when you consider n equal to 1. Okay, so we are going to stop this lecturette right here. So in this lecturette, I introduced you to some families of continuous random variables, and those were uniform, exponential, and the Erlang random variable. So in our next lecturette, we are going to solve some problems related to these random variables. Now, before I let you guys go here, let me give you the solution for the in-class participation problem for the Friday's class. You should get expected value of an exponential random variable as 1 over lambda squared, and you should get n over lambda, 1 over lambda, and the variance of an exponential random variable as 1 over lambda squared. What you need to do is practice your integration skills to verify that you get the expected value as 1 over lambda and variance as 1 over lambda squared. All right, guys, I think it's a good time to stop this lecturette.